All right, welcome ladies and gentlemen. This is our second video in the electrochemistry series on standard reduction potentials and cell voltage. First up, cell potential. What is it? Well, you're going to hear this phrase cell potential a lot in this unit. It is sometimes referred to as cell voltage, and that's exactly what it is. Sometimes you will also hear it referred to as the EMF of a cell. It is the amount of voltage that a cell is either capable of producing or the amount that would need to make it run. Right now, we're still talking about voltaic cells, and with that in mind, the big point about this thing called cell voltage or cell potential is that cell voltage is going to be positive for a spontaneous reaction. Every time we have a spontaneous reaction, we will have a positive value for E cell, which is how we abbreviate cell potential. So that's a really, really, really big point. Now, you should be thinking like spontaneity. We're thinking about spontaneity. So yes, we're going to bring in thermodynamics, and we have to be a little bit aware because in thermodynamics, predicting spontaneity or sine and delta G is negative. But in the case of cell potential, we're actually looking for a positive value to indicate spontaneity, because it's about essentially how much voltage can the cell actually produce. What is the number of volts that the cell can make, which is why we have this positive value. And we talk about cell EMF, cell potential, sometimes in terms of standard cell potential. So we standardize our conditions, and these are the exact same standard conditions that we have from thermodynamics. 1 molar solutions, 1 atmosphere pressure, 25 degrees Celsius. And we show that as E naught cell, right? So right here. So we see that, and it simply means that we're talking about standard cell potential. If we removed the naught, it would be simply under any possible condition. So if you just had E cell rather than E naught cell, it would not be under 25 degrees Celsius or 1 atmosphere pressure. Just as an example to show you with a reaction, we have this zinc and copper redox reaction, and if we're using this for a voltaic cell, the E naught cell for this is positive 1.10 volts, which means that if you made a standard cell, so 1 molar solutions of everything with zinc and copper, you would expect that cell to produce 1.10 volts under those conditions. Again, it's producing that voltage. The voltage is being made. The positive sign is indicating that this reaction is in fact a spontaneous reaction. We determine cell voltage, cell EMF, cell potential through something called standard reduction potentials. And this is a reference thing. This is something that you look up. And these are all half reactions. They're all reduction. Notice that we define this in terms of reduction. Reduction is sort of our go-to reference table thing for electrochemistry. And they are standardized, which means that they're all under 1 molar solution, 1 atmosphere pressure, 25 degrees Celsius. Table 18.1 in your textbook has a listing of standard reduction potentials for a whole bunch of different reduction half reactions. I included in the handout also the list of standard reduction potentials that used to come on the AP. You don't get it anymore, but you actually don't need it anymore because basically they decided they're just going to give it to you in the problem if you need one of these standard reduction potentials. And I also gave you the listing of the standard reduction potential half reactions and the values from OWL. So basically you just have this reference of lots and lots and lots of different half reactions with their standard reduction potentials. It is all reduction. So if we consider the reaction on the previous page, the one with the zinc and the copper, for example, that copper reduction half reaction would be Cu2 plus 2 electrons goes to Cu0. That is that particular copper half reaction. Notice that we are in fact reducing the charge. And the point about this list of standard reduction potentials is right here. The more positive the value for the standard reduction potential, the more positive the voltage, the more electromotive force there is for that particular reduction half reaction to occur. Now, what that essentially means, the more positive your standard reduction potential value, the more likely it is for that process to occur. So something with a very high positive value for their SRP, for their standard reduction potential, means that reduction half reaction really wants to occur, that thing really wants to be reduced. For example, fluorine, right? F2 going to 2F minus. Well, that's reduction, but fluorine really wants to be reduced. It wants to gain that electron. So it would have a very high positive value for its standard reduction potential. It really wants to be reduced. Whereas if you considered, for example, like Na going to Na minus, sodium does not want to be reduced. So it would have an extremely negative standard reduction potential. It does not want to occur. This is simply table 18.1, which you also have as a handout, and it's in the textbook, and it's just a listing of standard reduction potentials. Just to show you that copper one that we were talking about from that first reaction, it's right here. So we have the Cu2 plus 2 electrons goes to Cu0, and we have a standard reduction potential of 0.34 volts. So it's 0.34, so it's positive, so it indicates that, yeah, there's definitely a push for copper to be reduced, and copper certainly wants to be reduced more than, copper 2 wants to be reduced to copper 0, than more than, for example, copper 2 wants to be reduced to copper 1, right? This is a less positive value, so that one of the more positive value is more likely to occur. Notice that right here, what's sort of noted with the lines is the standard reduction of hydrogen to hydrogen ions to hydrogen gas, and that's 0.00. That's our reference point. It's like scientists decided that they would set that at 0 and then have everything essentially compare to hydrogen. So that's our basis of comparison for all these SRP values. Manipulating standard reduction potentials. So if you have to flip a reduction half reaction, if you flip it around, you are going to get an oxidation half reaction, right? Because the opposite of reduction is oxidation. And when you do that, you have to flip the sign on your standard reduction potential. So this should feel very familiar to us, right? You flip a reaction around, you flip the sign on delta G, delta H, delta S, etc., because we do have an opposite process happening here. You flip E red, you get E ox, and you're going to flip the sign. That's free and clear. That should feel very comfortable to you. However, this is a huge point. If you have to multiply a half reaction by something in order to get a overall balanced equation, right? In order to get the electrons the same in both your oxidation and your half reaction and your reduction half reactions, you do absolutely nothing to your E value. You do not, if you have to multiply your reaction by something, you do not multiply your standard reduction potential by that same value. And the reason is that a volt, which is what the standard reduction potential is measured in, it's measured in voltage, is 1 joule per 1 coulomb. When you are multiplying a half reaction by a coefficient, you are changing the number of moles. Notice what is absent in the unit for the volt. There is no mole unit in the volt. So if you double the amount of moles, the voltage is like, that's nice, we still have the exact same process occurring. So the volts are staying the same. So you do not change the value of the your standard reduction potential if you have to multiply your reaction by something. And that's what is like the huge point here. That's what is very different about our E-RETs. And just again, a voltaic cell will run spontaneously if in the direction that gives you a positive value for each cell. So again, this is also different, right? A spontaneous process now has a positive value for each cell. So we really need to link these two ideas together. The spontaneity of a cell producing voltage, giving us volts. The way that we use standard reduction potentials is to calculate the overall cell potential, that first thing we talked about, for a voltaic cell. And the way we do it is actually very easy. It's very simple. All you have to do in order to calculate the cell EMF, the cell potential, the cell voltage, is to simply add together the standard reduction potential for the reduction process that's occurring with the standard reduction potential for the oxidation process that's occurring. Now remember, you would have flipped the sign on this, right? Because it's oxidation. So your oxidation process, you look it up in the table and you flip the sign, and then you simply combine them together. You add them together. So as an example, if we wanted to work out the standard EMF for this particular process, we'd need our list of SRPs, so make sure you kind of have that out because we will be looking some stuff up there. So we have a voltaic cell, and I noticed the direction of electron flow, right? It's moving from the zinc over to that particular anode, that particular electrode. So therefore I know that the zinc is the anode and this is the cathode, because electrons will always flow from anode to cathode. So therefore I know that at the anode, based on what I have in the cell, I've got zinc, and then I have some zinc aqueous, and it is going to be oxidation, because I know based on the direction of electron flow that the zinc must be being oxidized. So therefore I'm going to write this half reaction, right? Zinc 0 goes to zinc 2 plus 2 electrons. And now looking this up in the list of SRPs, if I look up this half reaction, but remember it's going to be reduction, so I'm going to be finding the flip of this. I'm going to be finding zinc 2 plus 2 electrons goes to zinc 0. So the E red for this half reaction is minus 0.76 volts, but this is E-ox, right? We're flipping this around. So the E-ox value for this half reaction is actually just positive 0.76 volts. And that's the one that we're going to be using. So we looked up the minus 0.76 because it's a list of reduction, but we know that this is oxidation, so we're going to use the 0.76. And for the reduction process, well, okay, this one needs a little bit more discussion. We know that this half cell over here is the cathode based on the direction of electron flow, but then you have to consider what's there. So what do we have in that half cell? We have H2 gas, we have platinum, we have HCl. Now HCl is not really HCl, right? HCl is really H plus and Cl minus. And from these four species, we have to work out what is the half reaction that is occurring. Well, I'm hoping that you can see that it is not actually going to involve the platinum, and it is not actually going to involve the chloride, because we do not have two versions of them. But we do have two versions of hydrogen. We have H2 and we have H plus. The platinum is simply there to serve as a conduit for electrons. It is not actually taking part in the reduction half reaction. The reduction half reaction, and likewise the chloride is just there to kind of give us the H plus ions. So instead a reduction half reaction is going to involve H2 and H plus. So we want to write a reduction half reaction. So I'm going to write the H plus being reduced, right, going down in charge. And this is reduction. So looking that up on our list of SRPs, and that's actually our basis for comparison. That's 0.00 volts. And I don't have to flip that around. So if I want to simply calculate the EMF for this cell, right, E cell equals, as it says right here, E-ox plus E-red. So what's E-ox? 0.76 volts plus E-red, 0.00 volts. So this cell has a cell EMF of 0.76 volts, and that's how it works. And just another example so that we feel really comfortable with this, because this is a big important point here. What would be the voltage of the following voltaic cell? And we have a half reaction, or we have a full reaction. We want to write the half reactions. That's how we're going to work it out. So separating this out into the half reactions, we have Fe3 plus goes to Fe2 plus. Balancing that, I'm adding one electron on the left. And then we have Cu solid goes to Cu2 plus 2 electrons, adding the electrons there. Notice that this is actually not a balanced equation, but that's okay. I really just need the half reactions. So looking the stuff up, this is reduction. This process right here is reduction. The iron is reduction, so this is the cathode. So I can look up this half reaction just straight off of the list of SRPs. Be very, very careful that you find the correct one. You want Fe plus 3 going to Fe plus 2. You don't want Fe plus 3 going to Fe0. You don't want Fe plus 2 going to Fe0. You want very specifically this one. So E red, finding this, is positive 0.77 volts. And then looking up the copper, this is oxidation. So this is the anode. Now you're going to be finding the flip of this reaction because it's a list of standard reduction potentials. And when I find this reaction, the E-red value is positive 0.34 volts, but we don't want E-red, we want E-ox. So I'm going to flip it, and the E-ox value is therefore negative 0.34 volts. Again, E-cell is simply E-ox plus E-red. So we're going to add together the negative 0.34 volts for the oxidation process and the positive 0.77 volts for the reduction process, and we get an E cell of positive 0.43 volts, which is good because it indicates that it is a spontaneous process, and this is a voltaic cell, so we know that E cell will be positive, which it is. If you are not told what is oxidized and what is reduced, you can still use this list of standard reduction potentials to figure it out. The process, if you know you have a spontaneous process, right? If you know that your process is happening on its own, if you know you have a voltaic / galvanic cell, because galvanic is just another word for voltaic, then you use your list of SRPs to correctly work out which one was oxidized and which one was reduced. The half reaction with your higher E-red value will be the thing that is reduced. And when I say higher, I mean more positive. They could both be negative, and you're still picking the one that's more positive. Your higher E-red value will be reduced, and it will force the other metal to be oxidized. So we can use this thing because that way we will still have a positive E-cell value when you combine them. If you keep your more positive reduction process as reduction, and then have the more negative SRP value as oxidation, when you add them together, you will get an overall positive E cell. So that's our big point there. So for example, what's the standard EMF of a voltaic cell made of cadmium in a 1 molar cadmium 2 nitrate solution and a chromium electrode in a 1 molar chromium 3 nitrate solution? So this is an example where they're not telling us what is oxidized and what's reduced. We want to start by working out half reactions based on what we have in the cell. Now we're going to write these as reduction because we have a list of SRPs. So we're going to write both half reactions as reduction here. So what do we have first? We have cadmium in this cadmium nitrate solution. And I can tell by the fact that there are 2 nitrates that this cadmium must be a +2. So if I have cadmium 0 and cadmium +2, then I'm going to write the reduction half reaction, right? CD2 plus 2 electrons goes to CD0. And then I'm going to do the same thing for the chromium. So this is chromium 0. Based on the fact that there are 3 nitrates here, I know that this must be a +3 chromium. So therefore, this is Cr3 plus 3 electrons goes to Cr0. So these are the list of the 2 standard SRPs that I'm going to be looking up based on the half reactions that I know are occurring. Now I know that one of them is going to be flipped, but it's still going to be these 2. So looking up the SRP values. The cadmium, I find, has an E-red value of negative 0.40 volts, and the chromium has an E-red value of negative 0.74 volts. And recall that it says right here we have a voltaic cell, so that means that E cell is positive. So which one's being oxidized, which one's being reduced? The cadmium has the more positive E-red value, which means that there's more push to reduce the cadmium than there is to reduce the chromium. So I'm going to keep the cadmium as being reduced, and therefore I'm going to flip the chromium. The chromium will be oxidized. I'm going to flip the more negative one. So calculating E cell then, I'm going to have, E cell equals E-ox plus E-red. So flipping the chromium, I'm going to have positive 0.74 volts for the chromium plus the negative 0.40 volts for the cadmium, and the overall E cell here is going to be positive 0.34 volts. But I'm actually going to continue with this problem because I want to make another point. The overall balanced equation, if I want that, Then I'm going to go back to the half reactions, right? And I know that the cadmium is being reduced, so I'm keeping the cadmium half reaction as is. But I know that the chromium is being oxidized, so I'm going to flip that around. I'm going to write that as, Cr0 goes to Cr plus 3 electrons. If I want the overall balanced equation, I have to make the electrons the same on both sides. Right now, they're not. So I'm going to multiply the cadmium half reaction by 3 and the chromium half reaction by 2, and I'm going to add them together. So I'm going to get, after I do that, when I multiply the cadmium by 3 and the chromium by 2, I'm going to get 3Cd2 plus 2Cr0 goes to 3Cd0 plus 2Cr plus 3. What I want to point out that although this is absolutely 100% the overall balanced equation, the fact that I multiplied the cadmium half reaction by 3 and the chromium half reaction by 2 does not at all impact the standard oxidation potential and the standard reduction potential for these two half reactions. You are not multiplying the chromium half reaction SRP by 2 and the cadmium SRP by 3. You do not do that. Yes, you have to do it to the half reactions, but you are not going to touch this 0.74 volts and this minus 0.40 volts. Those are locked in because they are not dependent on the amount of moles that you have. So that's a really big thing that, yes, I did have to multiply these half reactions by something, but I am not at all changing or altering the value of the standard reduction potential in order to get a full balanced equation.